Beatrice's master thesis.
Thank you.
And opponent will be Veronica. And Solitary new classes. France.
France is unfortunately not here. He's preparing to go to Afghanistan for his new job, but he sent me a list of questions and I have agreed to raise them.
Sounds good. Great. Yeah.
Okay, first of all, I think most of you in here know my name, Beatrice. I know all of you, which is nice. And thank you so much for coming here today. I'm going to talk about my master's degree project here at Uppsala University. Its implications of magma and bedrock interaction, a study of Xenopumice from Palma, the Canary Islands. And I've done this thesis together with my supervisor, Professor Valentin Troll, but also together with Harry Jägerup. And as Jacob said, France is my subject review. So, why this study? This is the two most recent eruptions on La Palma. So here we have the Strombolian vent at the Volcano-Talks, occurred in 1971. Here we have a phreatomagmatic explosion on the summit of Cumbre Vieja, and it occurred in 1949. So I think like one of the main questions you can raise here is that why do we have this type of eruption, but also this type of eruption in the same island with this short time span? Because this is the common case, the Strombolian type vents. And as you can see, you also have Strombolian vent at 400 meters above sea level and the phreatomagmatic one at the top, so almost at 2,000 meters in elevation. And these type of phreatomagmatic eruptions occur usually when you have a magma interacting with water. And these can be explosive. So when you have the water interacting with the magma, you get expansion of the water to a gas, and you quickly expand this and you get fermentation of the magma, and therefore you can have these explosions. And this can increase with a factor up to 1,000 in volume. So it's quite a big process. And there are several of these type of events that are recorded on the Canary Islands, but the thing is that these mechanisms are not very well understood. And it's obviously important to know why or if you're going to have an explosive eruption, to think about risk assessment, right? Big explosion, dangerous. Vent, not so bad. And why these are not understood is that we have this dry climate, and meaning that we don't have much groundwater, because you need water to have these phreatomagmatic explosions, right? And we also find these phreatomagmatic explosions on odd places, for example, on ridges. For example, in this type of ridge. So there must be something we're missing if we don't have that much water. What explains the phreatomagmatic events? So Caricero et al. Started to think about this in 2015 in a paper where he drew a correlation between the occurrence of Xenopumice and also explosive vents on the Canary Islands. And this holds true also for the La Palma eruptions. So we have two sites, the 1949 eruption of Cumbre Vieja on the ridge, and also a prehistoric eruption at Las Indias. It's about 3,500 years old. You have the phreatomagmatic events, and you also have the Xenopumice. So Xenopumice, I brought a little sample here, where this, this is like really light, pumiceous, frothy rocks that are usually very light in color, so they have a different composition than the mafic coast lava. And we have occurrences of Xenopumice, for example, on Gran Canaria, but also on El Hierro. These have been confirmed sedimentary. By the Xenopumice on La Palma, we don't really know much about them. We don't know their origin, and we don't know how they formed. So the aim of this project is to, first of all, see what origin do the Xenopumice actually have, and is the formation of Xenopumice a process that's linked to the eruptive mechanisms and the eruptive behavior? And can we strengthen this link to explosive volcanism on the Canary Islands? So I used several different methods. First of all, we went to fieldwork on La Palma in December 2018. Went there with a group of researchers from here, but also from other universities. So we studied geological features, and we also sampled both Xenopumice and also phonolites. I'm going to get to the phonolites in a bit. And we also studied petrographic characteristics using thin sections, normal optical microscopy to see what mineralogy we had, what textures. We also used scanning electron microscope and electron probe microscope to see mineralogy and textures in better detail. And we also wanted to estimate density and volumetric change in the sample, how much they had expanded. And we also looked into elemental composition. So major and trace elements for a whole rock, just the cenolith, not the rim outside. And that was done at activation laboratories in Canada. And finally, oxygen isotope analysis. So we wanted to compare the oxygen isotope signature in the Xenopumice, but also in these phonolites, because the Xenopumice is frothy. Some of these phonolites that we picked up are also frothy, so they've also expanded. So we wanted to see if there was any correlation to increased oxygen isotope ratios compared to frothing. So that was a good proxy to see how good this method was to use for deciding origin of the rocks. This was done by Professor Chris Harris at the University of Cape Town. So geological background. The Canary Islands, you think of it as a tourist paradise, I guess. Palm trees, nice beaches. This is actually like one of the most researched volcanic island chains. And it's intraplate volcanism. Most people argue it's a hotspot, even though it's a bit debated, at the northwestern coast of Africa. And La Palma is the second youngest island, so it's still in its shield building phase. And I don't have an image of that, but the whole island chain is underlain by a thick sedimentary cover and also a mid-ocean rich basalt. In La Palma, the oldest subaerial volcanism, the volcanism actually occurring above sea level, is about 2 million years old. That is exposed in the north. It's a very, very steep and high island, so the highest elevation is about 2,400 meters and steeply dipping flanks. And this steep topography have led to several giant landslides during the geological history. And as I said, to the north is the old shield volcano. Here's the Cabrillanted crater and some dikes. And you also have the active ridge in the south, which is Cumbre Vieja. So you can see it here, also the topography. And this is the focus of the study. It's the active volcanism on La Palma. So therefore I'm just going to show you this magmatic trend. Basanite, that's the most primitive magma that we find. You also have up to phonolite, that's the most evolved magma that we find. The whole magmatic trend is silica undersaturated, meaning that quartz wouldn't occur in the magmatic rock naturally. And the studiers are located, as I said, in the Cumbre Vieja ridge here. And we visited the prehistoric eruption of Las Indias, but we also went to all the 6 historic eruptions that have occurred during the last 500 years. And the 3 areas where we sampled was these. See, quite close here. So going into the sample areas, we have the Las Indias eruption. So this is the vent of the eruption, like Alderata de Las Indias, but I think you can actually see it's quite a big explosion, and you have ash everywhere here. And this occurred about 500 meters above sea level. And the phreatomagmatic explosion, which was a high energy event, was followed by a Xenopumice rich lava flow. The site is also being quarried, hence we have Harry posing here by this wall. So there's a lot of places that uses this rock, especially in the south of the island, as building material. And the 1585 eruption of Jelly, where we sampled the phonolites, because you had the basaltic primitive magma of the tectophonolite, more evolved and more vicious magma. And the later pushed up an old phonolitic dome. And we can see the dome today as spines. And they are much older than the actual volcanic event in 1585, about 34,000 years old. And finally, the final sample area was the 1949 eruption of Canary. So it was from June to July, and it occurred at 1,800 meters above sea level. And you have 3 eruptive centers. The 2 most important are Durasneo and Oyonego. They have most of the magmatic activity. You can also see the big crater of Oyonego here. And most of the cenoliths did erupt at Durasneo here during the final phase, the last part of the eruption. So this is the magmatic ash layers of Oyonego and the crater. So you can see here, very, very fine-grained material, nicely layered, and these lava bombs with the impact sag, wet eruption indication for it. And quickly into results. This is from the field work. Here is the stratigraphy of Las Indias. So you have magmatic ash here, and explosive breccia. And above this you have this Xenopumice rich lava. So you can see all the white specks in the lava is actually Xenopumice. And as it had been quarried, we could also find very many, like a lot of loose species on the ground, which we picked up. And we also sampled this magmatic ash as a reference. And from the 1585 eruption, we sampled a different topography. So here we have the less affected phonolytic spine, very sharp edges. We also picked up for blocks in the lava flow, a bit lower down in the topography. And finally, the frothy phonolites. You can see they're quite frothy at the edges, and you still have like pristine center. But they've been heavily affected by the lava. So yeah, sample up here, that was hard. And also down in the valley. At Durasneo, we took Xenopumice from this little lava spatter field, and we also sampled ash from Oyonego. So here's the lava spatter field. I presume one of the later deposits formed during the eruption. And the other historic eruptions, so yeah, Volcano-Talks, the most recent one, you know, the typical Strombolian one, has basaltic composition, no main explosivity. Southern tip of La Palma, we did find Xenopumice, but they were very, very tiny, found them in this little lapilla field. But they were too small to actually conduct any analysis on. And for the other historic eruptions that we saw, 1646 to 1712, this is Louise from one of the lava flows. No Xenopumice at all. So these are the samples that we brought back. So 18 samples from Las Indias, 11 from the 1949 eruption, and 9 samples of phonolite that have different textures. You can see they're quite similar. You have this really light color, they're frothy, some are a bit weathered, but in general very similar. But when you look into the petrographic characteristics, they are not so similar anymore. So the Las Indias eruption has a main mineralogy of quartz. So this is how basically every single sample looked like. Quartz, glass, and bubbles. The black stuff here is bubbles. So the vesicularity ranges from about 50 to 80%. So it's a very, very porous rock. And the glass content as well, we didn't find much crystals, most of it was glass. In comparison to the 1949 eruption, we had mostly feldspars in most of the samples. And you also had a bigger difference between the vesicularity was from 5 to 50%, so some of them were not that frothy, and also glass content was lower in some of the samples. But the important part here is that 2 of the samples from the 1949 eruption contain quartz. So this is to show you the differences in between the 1949 eruption samples as they were different. Here we have a quartz grain in one of the samples, and here you have the mafic rim. And then you have a lot of vesicles going around in the sample as well, so it's very frothy. In comparison to this one, here you have feldspars, and you have these kind of like small vesiculation along the grain boundary. So there's not, it started to frothy up, but it's not really frothy yet. And it also has these triple junction grain boundaries, which is a very, very strong indication for magmatic. But I will go back to that later. because we will look into phonolites as well, and they were phonolites. This is feldspars, hyene, amphibole, also found in titanite. It's porphyritic, looks very much the same in every single sample, so we know they're phonolites. They had a lower glass content, but they had like a similar viscolarity with from 5 to 50%. And if you try to see how much do these samples actually expand, so we go from this to this. And if you use an average density 2.6 for glass, this was just to estimate this, as a lot of the samples had much glass in it. You can see that the density decreased down to 0.86 for the Los Indias, and for the 1949 eruption we have down to 1.09. And this corresponds to a volumetric change of 360% for Los Indias and 240 for the 1949 eruption, meaning that it expanded roughly 4 and double the amount of the first volume. And geochemistry. So remember now that 2 of the samples from the 1949 eruption just contain quartz. This is a task diagram, so here are the total alkalis and the SeO2. And we have some reference values you can read here. But focus is on the Los Indias one. You see many of them plot here in the rhyolitic field because they have a high silica content. And if you compare this to the rhyolite, which has less silica, but also higher in alkalis. And as for the trachytes field, you have trachytes and cyanite, but you also have some of the 1949 eruption Xenopumices. But the Xenopumices from the 1949 eruption do plot very differently. So when you track on the cyclone basalt, and here we have the 2 samples containing quartz. So they also, again, don't really match up with the rest of the samples. And phonolite plots as, which show phonolite and ash and lava plots as bastonite, which is also expected for this volcanic system. And this is similarly to TAS, uses the alkalis but also calcium oxide and silica weight percentage, and it is for phosphoric rock. So you had to exclude some of the samples that had lower silica content, as the ash and the lava. And here you can see the Los Indias also grouped together again, also a bit far away from the magmatic reference values. And then you have this group of 1949 eruption that plots together, and then you have these 2, again, the quartz bearing satellites from the 1949 eruption, not plotting together with the other in the group. And if you look into the rare earth element distribution, so this is the rock concentration in ppm divided with the normalization factor for chondrite. And on the x-axis you have the rare earth elements starting with light here and going down to the heavier. And for Los Indias, everyone plots basically the same. They have an enrichment in light rare earth, a depletion in europium, and also a slight increase of the heavier rare earth. Compared to the Los Indias samples, or the 1949, sorry, that goes from a high concentration in light rare earth elements and a positive anomaly for europium, and then an increase. But they plot not as nicely as the Los Indias samples. So these groups show very strong difference between the distributional trends for these samples. But once again, the quartz-bearing Xenopumice from the 1949 eruption plots exactly with the Los Indias samples. And finally, oxygen isotopes. Here we have sedimentary xenoliths. We have the ash, the phonolites from the 1585 eruption. We have lava from the 1585 eruption. And then we also have the Xenopumices from the 1949 eruption and the Los Indias. And what we can start with is, I think, the Los Indias samples. They have a very high oxygen ratio. It's from about 11 up to 18. And it's consistent, so all plot above 10 up to this. So they group very nicely together. And you can see these are the sedimentary xenoliths. They also have high values of oxygen isotope ratios. And if you compare this to the expected value of a sedimentary rock, you would end up between 10 to 30 per mil, which you see these two consequently plot correspondingly to. If you look at what magmatic rock would have for an oxygen isotope ratio, you would go from the mean mantle value, which is about 5.7 here, and maybe increase that with 2 per mil, 2 or 3 per mil, up to about 8, which is this. And you see most of the samples from the 1949 eruption end up here. As for the lava, as for the phonolites. So we have some outliers of the phonolytic group, but this does not correspond to the textures, does not correspond to the vesicularity. So there's some other process that have caused this elevation in delta 18 oxygen. And let's see, no, I'm going to show you. So these two samples here, which also have a relatively high oxygen isotope ratio, are the ones that contain quartz. So they have consistently been similar to the Los Angeles samples. And if you plot this with the silica content and versus the oxygen isotope ratio, you see that the magmatic values group together, and you see that the non-magmatic values of oxygen isotopes group together as well. So this shows a quite strong correlation between the high silica, the samples with high silica do not group together with the ones with lower silica, and they do not show that much in difference, or they show quite a big difference in between what oxygen isotope ratio they have. So into discussion, origin of the Xenopumice. Is it igneous or is it sedimentary? Well, it's important to know this because if you have sediments and you incorporate that in magma, you would expect the sediment to have up to 20% of pore water. This will, of course, add to the gas budget and potentially be more dangerous to add to your magma conduit. And I think that most of the samples with quartz, especially those from Los Indias and from the two from the 1949 eruption, are all sedimentary. And this is because there's quartz. You don't find that as a magmatic mineral in the rocks. But they also correlate with the total of the whole weight percentage of the rock has high silica value. So this is in general higher than the rhyolites that you have from Gran Canaria. And if you combine that with the oxygen ratios, they are also high. And the rare earth elemental trends were also correlated, and you didn't really see much correlation between rhyolite. They were not overlapping. And for the magmatic rocks, I think that we have 9 samples from the 1949 eruption that are magmatic or igneous, because they constitute of felspar, which is like a common rock-forming mineral on the Canary Islands. You would expect lots of felspars in your sample. But you also have these really nice triple junction grain boundaries, which form when you have a magma body that cools down, and you form these really straight lines, and also the triple junctions. So this is one of the biggest kind of evidence for it's actually magmatic. But you can combine this with the silica content, because they have a lower silica content. They also have a lower oxygen isotope ratio. And if you include the phonolites, you can know that these are magmatic. And they didn't show any general increase in the oxygen. And we could actually, so we can say like, if you have these really high values, they were probably sedimentary. If you have lower values that correspond to magmatic rock, they're magmatic. And what implications do we have then for the eruptive mechanisms? So we don't have any actual evidence for what the water source was for the Las Indias eruption and the 1949 eruption. And that's mainly because this 1949 eruption occurred very high up in the ridge. And the steep slopes, you wouldn't have any groundwater accumulation there. And Las Indias is also on quite a high elevation, so seawater would not maybe be the cause either. And you could see the Strombolian vent on Tenegia was actually on lower elevation and did not have any phatomagmatic eruption. And field evidence also show for you only have Xenopumice on the explosive vent sites. So if you have something from the bedrock here hopping into the magma conduit, this is a diagram from Figure 2005, and he did a study on the pumping system of Canary. So he concluded that you have underplating and stagnation of magma in chambers quite high up in the crust, so where you have the sediments, which allows for quite a substantial interaction between both bedrock and the magma. And these samples have degassed. So here you have the vesicle network of one of the Las Indias samples. This is very frothy. This figure from there, I'll show you how you form this vesicle network. What you do is you have continuous degassing, and you get gas migration, which you can see in the vesicle trails. And finally, if you put a lot of sedimentary stuff or felsic stuff that will degas, we know that we have a factor of volume increase of 2.4 for the 1949 eruption and 3.6 for the Las Indias. So say that you have 10% of Xenopumice in your magma, and then you start to degas that during decompression maybe and heating. This would increase the eruptive volume, only the eruptive volume, to 14%. And then you need to think about that you also increase the gas pressure. And for Las Indias, you have an even bigger increase. So we inflate them almost 4 times, you will have 26% increase of the eruptive volume. So eruptive volume and gas pressure will be larger than if you just had a magma conduit going through without any material added into it. So to conclude this, we have sedimentary and we have a magmatic Xenopumice. And we do see that the Xenopumice is restricted, at least in large amounts, to the sites with explosive activity. And we see that they have degassed, meaning that you increase gas pressure and eruptive volume. You also increase the risk of explosions doing this. And therefore, I think we clearly can say that Xenopumice formation might be able to explain why we have these phatomagmatic eruptions in other places on the Canary Islands where we might not have water causes. Thank you for listening.